This podcast is brought to you by LMU Munich.
Dmitry Trofimov, who is team leader and developer at PyCharm, and who will instruct us on how to do the undoable, in particularly how to profile the unprofilable. Please.
Thank you very much. My name is Dmitry Trofimov. I develop PyCharm IDE, and my talk today won't be about PyCharm. If you want to ask questions about PyCharm, come to our booth. And today I'd like to tell you about profiling. And who of you uses profiling, by the way? Oh, that's great. So we have a perfect club of people who like to discuss profilers early in the morning. That's wonderful. And why is it profiling the unprofilable? In this talk, I want to show you how to approach the difficult problem, which is seems to be unprofilable at the first place, but still we can we'll find a solution how to profile it, and then I'll show the logic behind how to optimize things in Python. So let's begin. As it happens quite often in our work, in software development, we start with an issue in bug tracker. So that's a real issue in PyCharm bug tracker, and it says that there is a code sample, and if you try to debug it, if you place breakpoint inside this function, the debugger starts to work very slow. So it works like minutes instead of seconds when you run it normally. And what do we do with that when you get this issue? But before, I will tell you a couple of words about PyCharm debugger. As our topic is to optimize the debugger, let's dive a bit into it. By the way, who of you understands approximately how debugger works? Wow, that's also quite nice. But for others who don't, I will say briefly about the debugger, and if you want to learn about it more, you can listen to my talk from EuroPython 2014 that's called Python Debugger Uncovered. There I explain deeply about how debugger is implemented. And the debugger that we'll be talking about is an open source project that is a Python project written in Python, and it's debugging backend shared by PyCharm IDE and PyDef IDE. Also very interesting project. If you're interested, you can just read the code. So we are speeding up the debugger, and here is the debugger architecture. PyCharm debugger consists of two parts. The part on the IDE side, it's a visual part, and the part on the Python process. So they communicate between each other. And the visual part, it displays you events and allows you to interact with the process being under debug, and the core part of the Python process, it generates events and handles breakpoints and so on. So I think it's pretty much clear. It's like on the Python side, it's a complex Python application, like with threads, and there is a trace function, and this all there can have overhead, but we don't know where exactly. I said the trace function. I'll explain what is this. So at the core of the debugger lies the thing that's called trace function. That's actually a window through which the debugger looks into your code. Python standard library provides you this API to develop tracing and debugging tools. It's called syssetTrace, where you can pass a trace function. And that trace function gets events that generates your program. So, for example, when the line is interpreted by the Python interpreter, this trace function gets that the line event that's the line is interpreted. And that allows us to build a debugger. And that is the example how it can look like. It's a trace function, and for example, it gets an event about a line, and we check inside that what was the file name, and do we have breakpoints for this file, and if you have breakpoints, then we handle it somehow. So that's briefly how debugger works. So let's go to our ticket. If we structure it, it looks this way. So our ticket is performance problem, subsystem debugger. If we run the code sample, it runs for 3 seconds. If we debug it, it runs for 12 seconds. But if we put breakpoint inside the function, then it runs for 18 minutes. That is what is unacceptable. And we kind of need to do something with that because it's unacceptable. And that is the sample code. It's a very simple piece of code. The only thing interesting here that in the middle we have the iteration through a quite big range. But yeah, nothing special actually. The first thing that we need to do when we handle an issue, of course, is reproducing. So we reproduce this example and see how it behaves. And then after that, after we reproduced it, we analyze the issue. And here we have 3 cases, like it's normal run, debug without breakpoints, and debug with breakpoint. And actually, if we will continue our analysis, we will see that the third case is actually 2 cases, because the breakpoint can be inside the function that you debug, or it can be not in the function, but somewhere in the same file, and that also affects performance somehow. So even if we put the breakpoint in the same file, but not in that function, still it works very slow. So these are our 4 cases, and the first 2 work fast, and third and fourth is have unacceptable performance. What do we do to improve it? And everybody knows the saying that you can't improve what you can't measure. So the first thing that we need to do if we want to improve something, if we speak about performance, we need to set up a measurement. And our measurement will be quite simple. We will just use module time, and we'll just record time before the loop, and then we print it afterwards. And if we measure it, we have approximately those values. So it's 9 seconds for debugging and very, very low for normal run. But the question that arises is whether it's really slow. Maybe it's not a problem of a debugger. Maybe it's just some strange case. Maybe it's not possible to do any better. How do we know that we even can optimize that? And to know that, we need to compare our application with something, and that's called benchmarking. So we take PDB to benchmark our debugger, because PDB it's a bit less functional, but it still has basic functionality that is sufficient for our case. It's also written in Python. It is in standard library. So let's compare our application that we want to optimize with PDB. And after we run our measurement on the PDB, we'll get these values. So we see clearly that PDB is also affected by the same problem. So if we put breakpoint in our sample code, PDB starts to work significantly slower. But still, we see that it is a bit faster than our debugger. And that means that we can optimize our debugger at least to be as performant as PDB, or maybe to outperform it. So what do we do next? After we set up our benchmarking, we need to optimize things. But to know what things to optimize, we need to find a bottleneck. So it doesn't make sense to optimize something irrelevant. We need to find a bottleneck and then optimize it. And to do that in the most efficient way, we need to profile. So we just need to know what what part of the program takes the most time. And that is exactly what profiling is. So profile is just a set of statistics that describes how often and for how long the various parts of the program run. And the most obvious choice to profile things in Python is, of course, cprofile, because it is part of the standard library. It's written in C, and even in documentation it's written as default choice for Python profiling. So just let's take it and try to profile our debugger with cprofile. And we do it with PyCharm, because PyCharm has integration with cprofile. Okay, so that's our sample program. The same with benchmarking, and we run the profiling. We use this profile button, and we execute it. So you see that we have a breakpoint here. We resume, and we wait until finish. It won't be 18 minutes because the range here is smaller. Now we have our profile snapshot opened, and there is a statistics, and also we have a visualization on a graph. And let's look inside. What do we see here? So we see that yes, that's our script, and that's our function. It took long, but we can't see anything. We just see some strange calls that took almost 0 milliseconds, and we just don't understand what's going on because we don't have our debugger inside this snapshot. It's like we have only our application, but we know that our sample code works fast, and a debugger is actually who affects the performance, but we don't see it in this snapshot. So what do we do? So the question is whether our debugger is unprofitable. This question. And if it's so, what do we do? And to decide about that, to know whether it's unprofitable and what do we do, we need to dive a bit deeper and to understand how cprofile works. So cprofile actually is a tracing profiler. It provides a deterministic profiling in Python programs. And what does it mean? There are two types of profilers. There are tracing or deterministic profilers, and there are sampling or statistical profilers. And tracing profilers, they work by tracing all the events of your code. So it's like debugging, but you don't have breakpoints there, you have the measurement inside this tracing. And those profilers have disadvantage that they a bit slower because they introduce an overhead, because they trace every event. But actually you get the picture clear because they trace all the events and you can't miss something. But still, why doesn't it work for our case? Let's see how cprofile is implemented. As it was with the debugger, Python standard library provides us API that's called syssetProfile, where you can pass a profile function as we done it with the trace function. And as it is written in the documentation, so it's clearly written, it's similar as a trace function, that it traces every line of the user code. So that's quite obvious that if it traces the user code, then it doesn't trace the debugger, because debugger is not user code. So it's not possible to profile with that, to trace with that something that isn't user code. So what do we do? Is it unprofilable? So there is a good German word, Jein. So yes, it is unprofilable with C profile, but we know that there are other profilers, sampling or statistical profilers. And how do they work? They actually collect call stack samples regularly at the regular interval. So it's every 5 milliseconds, for example, they just capture the stack trace and dump it. And they add no overhead, and they dump stack trace for all code that is executed, no matter whether it is user code or it is our debugger implemented as a trace function. So they just dump the stack trace. So it might be that it is the tool of our choice, one of the sampling profilers. But what do we choose? There is a profiler called Vmprof. That's my favorite sampling or statistical profiler for Python. And it's implemented by the PyPy team. And it works for CPython and PyPy and for all operational systems. And it's written in C, it's very performant, and it's a nice thing. So let's try to use it to profile our debugger. We'll do the same, but now we'll run now we will profile it with the Python interpreter, which has Vmprof installed. So the same thing, we continue, and we wait until this thing finishes. And after that, we have a snapshot taken by Vmprof, and we have here call graph and also call tree. But let's look at the call graph and see whether something changed in comparison with C profile. And we see that here we have a hot path. So that's our script, and if we move here, we see that the most of the time is taken in the trace dispatch function, which totally makes sense because that is our trace function of the debugger. And we can see it's deeply in the call tree, so we can find it in the call tree. So yeah, we could find it, yes, here, like 60% of the time is taken there. And actually, it's quite the obvious result, but we just confirmed that, yes, tracing function is the villain here. So that is the thing that we need to optimize. And now we can really optimize it. Now after we know that that's the thing that had to be optimized. It's the thing called bottleneck. So we found it. Great. Now we optimize things. And what is optimization? Optimization actually, so it's obviously you make your program faster, more performant, but optimization is also not that strict because it can be done at different levels. And it can be done at a high level, it can be done at the low level. And normally, the higher the level of the optimization, the better it is. For example, the highest level of the optimization is a design level. You can change the architectural design of your program, and that influences the overall performance the most. Can we change the design of our program? Unfortunately, no, because with our debugger, we need to comply to the set trace API, so it's no way for us. The next level is algorithms and data structures. And on that level, you can improve your algorithms and data structures and make your program faster. Can we make optimization on that level? Let's think about that. Let's look at our trace function. So if you look into the code, we'll find out that in case that there are no breakpoints in the current file, the trace function returns none. while if there are any, it returns itself. So it returns trace function. Why is that so? We refer to the documentation again, and we read that the last paragraph, the local trace function should return a reference to itself. So yeah, I won't read it. How do we use it to optimize our trace function? We can just store the name of the function where breakpoint is placed. And when we don't have breakpoints for this particular function, there is no need at all to trace this function. We just can return none, and we just can give up the tracing in this context. So we just return none if there is no breakpoints for the function. And after we do that, we see that the fourth case starts to work as fast as debugging without breakpoints at all. So we've done our optimization of the algorithm level, so it's algorithmic improvement. Can it be done something else? Can we do better? The next level of the optimization is the source level. So after you optimized your algorithms, you can optimize on the concrete source code choices. But to do that effectively, you need to have line profiling. Because you need, of course, you can just look at the code and understand, okay, this is written not efficiently, I'll rewrite that. But if you can profile your lines, you can see that this line takes longer. Maybe I optimize this one. And let's do that because it's very great that Vmprof provides you with such tool. So you can profile even at the lines level with Vmprof. And we use again PyCharm for that. So we open our snapshot that we took before. And here we can navigate to source. And after we do that, we see that the lines are marked with the colors. And this red thing tells us, no, it doesn't tell us because of the resolution. But it tells us that it takes 60% of the time 60% of the samples. So this line is very ineffective. So we need to optimize, we can optimize this one. And actually, if we look what getUtter does in Python, we'll learn that it does a lot of things. So it checks the parents of the class and different dictionaries, and we just don't need it here. We just need here that an object has a field, not the parents, or that particular object has field, so we can rewrite it. So we can like write something thread. We can optimize it this way. That's not recommended to use it always, but it is good optimization in this particular case. And after we do that, we see that we have 1 second. We won 1 second. That's great. And so source code level optimization is done. So what do we do next? Unfortunately, Python doesn't allow us to have build, compile, and assembly optimizations because it's interpreted language. But is it so? Is optimization reached its limit? No, because we can actually go beyond Python. We can, for example, rewrite everything in C, but for this case, it's not good because then we lose compatibility with Cython, PyPy, and there will be code duplication because some parts will be written in Python, some in C. It's not good, and Python is a better language, so let's try to use Cython. Cython is a static compiler for Python that gives you the best of two worlds, actually. And it looks the same, you just add type definitions here. So we just add type definitions to our function, and we compile it, and yeah, now it is 4 seconds. And if we compare it with PDB, so we see that we've done even better. So just by adding some type hints, we now faster than PDB. So what we do is issue. Is it done? Yeah, we made it better, but still we can improve. Because the latest addition to Python 3.6 is this PEP. It allows us to customize frame evaluation, and using that one, we can even make debugging as same as performant as the normal run. So we'll not close this issue. We'll try to optimize it further. So the conclusion of this talk is use profilers to find bottlenecks in your code. And there are different profilers, tracing and sampling. They have their ups and downs. And stop to optimize things and use Cython if you want to go deeper. So that's all. Thank you very much.
Thank you very much, Dmitry, for this talk. We have a little time for questions. Are there any? Here's a question.
What would you recommend for profiling of online running application, like application which already runs and you would like to get a sample of some like to see what's going on there in real time?
So this is a question about, for the record, a question about how to what to do about an already running application.
About online or about web?
Yeah.
There is a tiny problem here that normally when you implement your web application, you use some framework. For example, you use Django, and in that case, you're normally not interested in everything that happens in Django itself. You are interested only in your specific view or your, I don't know, model transformation. And in that case,
but it's open source.
yeah, it's open source, but time is costs money. So of course you can read Django source code if you're interested, and it's good to do that. But sometimes you just need to optimize your application. And in that case, to profile everything, all the stack is not efficient because you will see the Django calls. And I recommend in that case to use special middleware. There are tools like that are called Django Profiler, for example. It is installed as a middleware, and it profiles only your views. Also, if you want to profile some specific part, for example, in Vmprof, you can just annotate some function, and Vmprof will profile only that function. But that involves change in your source code, but actually, normally you can afford that. Yeah.
There's one more question over there.
Can you attach a debugger tracer to a running process and start profiling the website that's online, regardless of the Django stack that might be behind that?
That is a question, again, for the record, about whether it is possible to attach a profiler to an already running process.
Yes, you can do that. There are tools that provide this functionality, but unfortunately, PyCharm doesn't allow you that now. And I know the tool that's called PyVMMonitor that allows that. That's a tool implemented by Fabio Zadrožny, the maintainer of PyDev Debugger. And you can use it for open source projects. It's free, and it allows you to attach a debugger to the already running process. And it uses C profile for that. And yes, this feature is our list also. So we want also to implement that in PyCharm, but we just didn't do that yet.
We have time for one more question over there, please.
Does PyCharm support debugging async.io applications?
This is a question about whether PyCharm does allow to debug async.io programs, applications.
Yes, it does, and we have like experimental feature and I will show you. It's called concurrency diagram. So you can visualize what's going on inside. So it's because the debugging of asynchronous application is not very efficient because you jump between your threads and coroutines. Of course, you can do that with normal debugging. PyCharm supports that, but other than that, there is a special tool that could be useful. So it's quite a new thing. It's experimental, but in some cases it helps.
So again, thank you very much, Dmitry. Thank you very much for the questions.
Thank you.